Here is the stuff I'm going through.
Monday or Tuesday? Monday.
Next week. Okay? So, first of all, we're doing types of energy, and there are two different types of energy, broad categories. There is kinetic and there is potential. Kinetic means moving, potential means storage. Under kinetic, the first one we have to talk about is thermal energy. For thermal energy, we're talking about heat. In particular, we're talking about kinetic molecular theory. Thanks, Triple H. Right. What this means is, as you increase temperature, you increase kinetic energy, which means the particles move faster. Therefore, you increase the speed of the particles, which means you increase the collisions. And it's the collisions that pass on the energy. Therefore, you increase the transfer of the energy. So all we're doing here is we're saying that as you heat something up, the particles move faster and faster and faster. And the movement of the particles allows it to change state. So we're going to go from a solid to a liquid to a gas. So you'll probably notice the table in front of you that's a solid doesn't look like it's moving very much. It's because it has the lowest energy. Then by adding more energy to it, theoretically, it can become a liquid, which has a medium amount of energy. And as it turns into a gas, it has the most energy. So you can change state by adding energy or taking away energy from the system. If the best example to think about is water. When you take all of the energy out of it, it becomes a solid as ice. If you add energy to it, it becomes a liquid. And if you add more energy to it in the form of heat, it turns into a gas. Yes? If you take away energy from a gas, it does become a liquid. As you take energy away from a gas, it becomes a liquid. Take energy away from a liquid, it becomes a solid. Yeah, but that's sublimation. Okay? I don't think so. That's more chemistry than physics. Sorry? We are going to keep going. Yes.
Is it true that the test is online?
Half's online, half's written. Okay? But I need to get through what I'm getting through. Roxy. All right. Add energy plus, go back this way, minus. Okay? So, there are three ways that heat can travel. There is conduction. There is convection. And there is radiation. Conduction is through a solid. This is where, if you heat one end, the heat will go from hot to cold. Okay, you should have done that experiment in class where you heat up a metal rod, and as you heat it up, the end that's far away from the flame should get hot. Okay? What's wrong with that, Mr. Laney? I'm going to continue. It's just a fact. You heat up one end, and heat conducts heat. All right. Convection is a convection current. Now, I know not every teacher teaches the same thing, and which is the reason we're here today, is to create a level playing field. All right? Now, I can't control what your teacher teaches you, so I'm trying to give access to everybody. Okay? So a convection current is where we have a heat source down the bottom here, and as it gets hotter, it rises, and as it gets colder, it sinks. Okay, it's called a convection current. Okay, as it gets hot, it rises, and the reason that it rises is the density gets lower, so it becomes lighter. Okay, as the density drops, it becomes lighter and rises, and over here, as it cools down, the particles get closer together, so it increases the density, and then it sinks, and it just keeps repeating. Yes?
Is there a certain point where it starts like going down?
When it gets to the top and away from the heat source, there's no more heat being applied, so it will lose it to the atmosphere.
Is it because the particles space out when it's down?
Yes, it's all to do with what I just taught you here. As you increase the amount of heat, the particles move faster, keep smashing into each other more, so they get separated more because they hit and they bounce off. So it makes it lighter because they're filling up more space, and so it becomes lighter and it rises. Okay? Radiation is when the heat, if there's the particles of the atmosphere, the heat moves between the particles. All right? So if we had the sun, and in space it's a vacuum, you would know we get heat from the sun, all right? And radiation doesn't need particles to be able to transfer the heat. It goes between the particles, which is how it gets to the vacuum of space between the particles of our atmosphere to hit you on the Earth, which is how you get sunburnt from the sun. All right? But it doesn't need particles. Yes? All right. Radiation goes between the particles. It doesn't need particles to travel. These two here transfer heat between particles. They're called mechanical. Mechanical means it needs particles to travel. So conduction and convection are mechanical. They need particles to travel. They need to collide with each other to pass the energy on. Whereas radiation can move between the particles. It doesn't need particles to travel. It's not mechanical. Yes? It goes between the particles of anything. Okay? All good? Right, so they're the three ways that you need to know that heat travels. So next on my list, I've got movement. And this is what you guys might be thinking kinetic energy is. This is the one that we can work out KE equals a half mv squared. Okay, you'll need to be able to do this calculation. And during the transfer, we'll go through this. Okay, but this is where m is mass. I think I just said that.
Like every equation is on
If you're given these equations, you need to know how to use them. All right? V is velocity in meters per second. Okay? You have to be able to calculate kinetic energy. All right? Yes. Meters per second. Sorry? Another way you can write this is ms minus 1. Okay? Gravity is different. That's an acceleration. Okay? That's just kinetic energy. You need to be able to use this equation. Right? Because if I said an object has a mass of 1 kilogram and it was moving at 1 meters per second, and it was asking you how much kinetic energy it had, then we would just use this. So KE equals a half mv squared, which equals a half times 1 squared, which is 0.5, and the units are joules.
Is it capital?
Capital J. Okay. Obviously, the question you're going to get is a little harder than this. All right? But you need just put the numbers in. You're given the equations. You need to know how to do it. Okay? So that's movement. Right? The next one is light. Now, light is interesting because it travels as both a particle and a wave. So when it's a particle moving, Mr. Laney, we're talking about photons of energy. All right? We're talking about the movement of a photon. All right? It carries the energy. All right? So that's why it's under kinetic energy. It's a moving thing. There are photons coming from the sun and coming down to us on Earth at the moment. All right? But it's also a wave because it's an electromagnetic wave, or what we call the EM spectrum. So there's the EM spectrum. Right, sends out a whole lot of wavelengths. Okay? So we can only see a very small part of the EM spectrum. So what we see colours, and those colours fit in there. All right, so it becomes Roy G. Bev. All right, they're the red, orange, yellow, green, blue, indigo, violet.
So this has the cut.
There are. So up here there is infrared, which is how heat moves. And down here there is ultraviolet, which is how insects see. So just because we can't see the wavelengths doesn't mean they don't exist. If we saw in the spectrum of gamma radiation, which is how sort of like Geiger counters work, we'd be able to see different sorts of energy, but we only see this small part we call the visible spectrum. Okay, so just because we can't see the light doesn't mean it doesn't exist. And we'll talk about that when we start doing friction. All good? So the electromagnetic spectrum is that we've got an electric wave going like this, and at right angles, we've got a magnetic wave going at right angles. But the interesting thing is that after it does one of these, it does one of these, and then it goes, so it swaps between the two at the same time. Yes?
Is this spectrum in the test?
Okay then, so I dare say you need to know about light, Roxy. Right, I'm going through the different types of energy, and your test is about energy. Right. I'm not teaching what's in the test. I didn't write the test. I'm teaching what the course is. Okay? But given that it's a test about energy, it's likely that some of this will be in it. Mr. Cotter. Right. So, then we've got sound energy. Sound energy is mechanical again. What does mechanical mean? Requires particles. So sound is about vibration. Sound is mechanical because it needs particles to travel, and the particles vibrate. Okay? So the way that it works is this. See, out of my larynx at the moment, my vocal cords are vibrating the air, and it's coming out in these bands of compressions, right? So where the particles are close together, we call them a compression, and where there's less density here, we call that a rarefaction. So the two words there are compression, which is a wave of the particles being close together, and in between there are spaces where the particles are less close together. So they're a lower pressure, and we call that a rarefaction. Now, because it's mechanical, it requires particles to move. So which type of matter has the particles closest together? A solid. So sound travels best through solids. Okay? If you go up to one of the columns in this library and you speak into it, the person, if they put their ear on the other side, will hear it very well. Okay?
Better than us talking through gas right now.
Better than going through a gas, because the gas particles are very far apart.
But we're talking through gas right now.
Correct. I'm not saying that gas doesn't allow the transmission of sound. I just said it travels best through solid. This is how whales, if anyone ever goes underwater, you can, sometimes if there's whales a kilometre or two away, you can hear the whale noises underwater, even though you can't see them. Because the vibrations go through the water very well. Sorry?
Oh, so basically, we're better to hear underwater than we are above water.
Yeah, so if I'm loud in the atmosphere, when the particles are far apart, imagine how loud I am underwater. Right. So here we can make a graph of this wave. Right, so we've got high pressure here, high pressure, high pressure. All right, that's a terrible graph. All right, we have here from the midline to the top of the wave, that's called amplitude, which equals volume. All right, can I have a rubber router? Okay, then we also have the distance. The distance from a crest to a crest is called a wavelength. The wavelength, so that how long the wave is, equals pitch. So if I have a short wavelength, that's a high pitch. If I have a long wavelength, that's a low pitch. Okay? Yes. Yes. But that gives you the frequency. A frequency is the number of waves per second. So if you've got a short wavelength, you can fit more into 1 second. Yeah? Thank you. So if you've got a short wavelength, which means you've got a high frequency, that gives you a very high pitch. I know. And if you've got a long wavelength, you've got less waves per second, and it gives you a low pitch. Triple H. Okay? Yes. Long. Short. Long. I'm trying to write on a board that's moving. Yes. Per second.
What's a crest?
Sorry?
What's a crest?
Top of a wave. This is a trough. This is a crest. A wavelength is just the length of the wave. So you can measure wavelength from here. You're up and down. So there's one wavelength as well. It's just one complete wave. The length of a wave.
What's the top of the wave?
All right. Then we'll get on to electrical. Yes, wavelength is the length of a wave. The longer it is, the less you get per second. Right, electrical is the movement of electrons. And they need to be moving through a circuit. Okay, as soon as you put an electron into a circuit, it's going to move. And normally we have a battery. Okay. Here's a circuit. Okay, there's a simple circuit. That's a light globe down the bottom here. I don't think in this test you'll need to be able to draw series and parallel and stuff. Okay. Sorry? I don't think you're going to need to do it. At the start of this topic last term, we brought down some stuff from year 9 because they're not teaching in year 9 anymore. Okay? But this is a battery and the electrons go from the negative electrode. They move through the wires. Here's the electrons. They go through the globe and they go back to the positive electrode. Okay, Triple H? Right. So it's kinetic because the electrons are moving. The electrons hold the energy. And there are devices that can use the energy. So here is a globe, and you would know that if you put a globe, when you turn the lights on at home, the globes go on and they use the energy. They don't use up the electrons, they use the energy in the electrons. Okay? Good with that? It's just a form of energy. But we'll talk more about this when we start doing the transfer. I've only got 15 minutes now. All right? Okay, and then static electricity is where you build up electrons on something. You might have done the Van de Graaff, where the electrons built up on the dome. Okay, and then you could zap it because the electrons could jump from the negative to the positive. Correct. Okay, the discharge of the electrons. All right, we need to get on. Yes. I'm going to keep going because we're running out of time. I only have a limited amount of time today. Okay? Potential energy is the storage of energy.
And kinetic energy
Is the movement of energy. Kinetic means movement.
Like kinetic.
Kinetic is movement, which is all the ones we just did, and potential is the storage of energy. So there is gravitational, there is elastic, there is chemical, and there is nuclear. We'll quickly go through them, okay?
Thank you.
All right, gravitational is when you hold something above the ground. So there's 2 meters tall and you're holding something above. All right, it has the ability to fall. You need to know this. You need to know how to use this equation. You're given the equation. So this is GPE equals mgh, where m is mass in kilograms, g is gravity, which is on Earth, it's 9.8 meters per second, otherwise known as ms minus 2. All right, and then h is height, and that's in meters. Okay, so you can work out how much energy something has by being held off the ground. Okay, elastic is the energy stored in a spring, okay, like at the pop ball that we did in class. All right, chemical, that's batteries. Whenever you have a battery, that's a store of chemical energy. Sorry?
Is like chemical energy like the main like starting off?
Depends on what you're talking about.
Like a light bulb?
Is it just
No, a light bulb isn't chemical potential energy.
Is it just like a battery?
Food or batteries are chemical potential. Sorry? Petrol is a good, all right? The storage of energy in a chemical bond. All right. Nuclear is the energy within the nucleus of an atom. All right, so this is the nucleus. And the interesting thing about the nucleus is if you add something to it, it will explode. And if you try and remove something with it, it will explode. So if you have fusion, which means to push things together, it will explode and release energy. And if you tear it apart, it will also explode and release energy. So anytime you mess with the nucleus of an atom, you're going to cause an explosion. You will get burnt / vaporized. Yes?
Then how do you get energy from nuclear energy without it exploding.
Well, that's why it's very dangerous.
And then
Okay.
how do you get energy from it without it exploding? Or it does explode.
It does, and that's the
Control environment.
we capture the energy of the nucleus decaying.
Oh.
Okay? So, we'll move on. It's all on the mind map. So, I can't go through the entire course. I can just talk about what you need to know. All right? So, the next thing we're going to talk about is LOCO. Law of conservation of energy. Means you can't create the energy. You can't destroy it. You can only transfer or transform. Transfer or transform. Transfer means from one object to another. Transform means one type of energy to another. This is what we're concerned with. The transfer and the transform of energy. So the simplest one that you guys need to know is, if I've got a ball at the top here, how heavy is the ball, Leo, in kilograms? 100. Right. M equals 100 kilograms. All right, there's the mass. Here is the height. How high in meters, Flo? Don't know any numbers? 2. 2 meters. All right. And then we know that gravity, so down here, so H is 2 meters. H equals 2 meters. And we know that gravity is 9.8 meters per second per second. All right. So the GPE at the top here, GPE equals mgh. M is 100 times 9.8 times 2. Okay? So that's 980 times 2. 196. Sorry?
1,960.
1,960 joules. That's how much energy that ball there has. All right? Are you paying attention, Mr. Lady? You need to pay attention.
I'm just asking.
You need to pay attention. As it falls, it converts the energy into kinetic energy. So GPE will get converted into kinetic energy as it falls. So let's do at 1.6 meters, at 1.2 meters, let's go at halfway, 1 meter, all right? At 80%, at 80% down, so there's 80%, all right? It's lost, it's still got 80% here, but 20% has been converted into kinetic energy. It's starting to fall. And as it goes further, so here it'll be 50-50. At halfway down, it'll be 50% here and 50% here. And as it hits the ground, as it's just about to hit the ground, all right, it's just about to hit the ground, it can't fall much further, or can't fall further, so it's got 0%, and 100% of the energy will have been converted to kinetic energy. Yes?
So does that mean that the ball's falling fastest when it's
Just about to hit the ground. Yes. Okay? That's very good. Yep.
Is GPE to K, is that energy transformation or energy transfer?
It's a transformation because it's going from one type of energy into another. Transfer is going from one object to another. So the same type of energy just changed from one object to another. Yes? We'll talk about them in a minute. At the moment, we're just talking about this. Yes?
Can you, like it just went to kinetic energy. Can it go to like 2 things at once? Yes.
Yes, but we'll talk about that later. All right. Now down here, I have to continue. I've only got a few minutes left. What you do need to know is how to work out the velocity at the bottom here. All right? So down here, we know that GPE has been converted into KE. All right? Which means that if we had 1960 joules at the top, it's now all been turned into kinetic energy at the bottom. So now this is 1960 joules. Now I'll show you how to do it, but you'll have to do this at home. But it's in the mind map. Now to work out the velocity, because KE equals mv squared on 2, half mv squared. All right? Is that okay? Now we transpose the equation. So V equals 2KE on M. Okay, just transpose the equation. So if you did the square root of 2 times 1960 divided by M, which was 100, it would give you the velocity in meters per second. Okay? Well, good. So now I'm going to quickly go on to transformations and efficiency for you. Okay? You need to be able to work out how energy moves from one type to another and from one object to another. Now, all of this is on the mind map except for the efficiency bit. All right? I'll just move this again. All right. Ooh, efficiency. Efficiency and transfer, but it all comes on the same thing. If you're going to go from GPE to KE, you're not going to get 100% transfer of energy. Okay? You're going to get, just say we started off with 2,000 joules of energy in something held off the ground. And you let it drop, and as it drops, it picks up speed. Now, it would be lovely if we had a 100% conversion of energy, but we don't. Okay? Just say over here, this ended up being 1,600 joules of energy. The question is, why isn't there 100% conversion? Yep.
Because some of the energy is converted to sound.
Yep, so we have friction. And in friction, it converts energy into heat, light, and sound, which are wasted forms of energy. Okay? So the efficiency is output on input times 100. So the energy that we want here is 1,600. 1600 divided by the input, which is 2,000 joules and joules, times 100, and that would be 80% efficient, which means 20% of the energy has been wasted. Okay? But this might change depending upon what you consider useful. You might think that the heat energy is useful, and so that would become the output. It all depends on what you consider the useful energy. Yes?
Is there ever a time where we need to find out like how much heat is wasted or how much light?
Well, they'll tell you some amounts, and then you need to use that to work out the efficiency. You do need to be able to do this for your test. It's one of the standard. Without me writing the test, I can tell you you'll need to be able to work out the efficiency of an energy transfer. Okay? Yes?
Will that give us such a formula?
Of what? Probably, yeah. It's not about whether you can memorize the formula, it's whether you can use the formula. Okay? Now, this was when we get up to the Sankey diagram. Now, in a Sankey diagram, the thickness of the line matters. So if I did this in a Sankey diagram, goodbye.
I learned a lot, thank you.
Wonderful. So here would be the input. This is the thickest line is the biggest amount.
Thank you.
Okay? Someone left their computer, boys. It's okay. Someone left their computer. All right. Now, only most of the energy here gets converted into kinetic energy. So this will be here 2,000 joules. Here is 1,600 joules. 1600 joules. So it has the second thickest line, but we know now, we don't know how much here is, so that's another 400. So we might say 200 is there, 100 is there, and 100 is there. So here we're going to have a line that's a bit thicker than the others are going to be, and then there's going to be a thin line and a thin line. All right, so this will be 200 for heat, this will be 100 for light, and 100 for sound. Okay, and that's the Sankey diagram. You need to be able to do them. Yes?
How do you know how much
it will tell you.
Do you label like which one's heat,
Yes.
light, and sound? Okay.
You label as much as you can.
And how accurate do you have to be with your thickness of lines?
I need to be able to tell the difference between 1,600, 200, 100, and 100, and 2,000. Okay? Just thickness of the line matters. It doesn't need to be exactly proportional, but your examiner, your teacher needs to be able to tell what you're trying to draw. Yes?
Did you make the 1,600 get like smaller from the
No, no.
2,000? Or not?
Yeah.
Okay.
I know it looks a bit like that, but I'm just trying to hurry.
Okay.
Sorry? This one needs to be the thickest. From there to there needs to be the thickest. From here to here should be about 80% of that line. And then these two, these three, this one needs to be the thickest of these three because that's 200. And these two need to be the same because they're 100 each. Okay? You need to label it with units of joules. And then you would say light, sound, and heat. Okay? The more information you can give to your teacher, the more marks you're likely to get. All good? Right. You do need to, I'll stay for another few minutes now that they're gone. Most of the noise has disappeared. Okay? One other thing that you do need to do is to be able to do the energy transfer diagrams. Okay? But this is where you need to think. This year is about learning how to think, because next year in year 9, if you haven't practiced thinking, you might struggle. Okay? Now I say practice thinking, some of you might think, I think all the time. But your thinking is using your knowledge to solve problems that you've not heard of before. Okay? So it's not saying that you don't think, but you need to think about how to use your knowledge. All right? So for an energy transfer, you might start off with a battery. Okay? And then that might get turned into electrical energy. Well, it does. Electrical. Oh, I've got a wet board. Electrical. So you're putting that energy into a wire. So this is chemical potential energy. That is kinetic energy. And then that gets into a motor, which again is kinetic energy. Yes.
Would that be a diagram of like energy transfer? Or
It is.
energy
Both.
transformation? Oh, okay.
Transformation, here is the transform from chemical potential into kinetic. You're transforming, but it's already in kinetic, just going from one object to another. That's transfer. But for most, in year 8, most of it is they think they're the same thing. Okay? Yes?
If the multiple the light bulb, would it be transforming into light energy?
All right, let's go down to here. If I rub that out, electrical, and we put a globe. All right, here we want light. So that would be light energy. But we also know when you put on a light globe, it gets hot. We have heat. And we get sound. The older the light globe is, when you switch it on, it actually makes a noise as it comes on. All right, so these are wasted forms of energy. All right, so heat energy is heat and sound energy is sound energy. Yes,
So when you draw this diagram, you include like the.
I would include as much information as I could. Yes,
Um,
the question might say to include the wasted forms of energy.
can chemical energy be kinetic, or is electrical energy the movement?
Can you ask your question again, because it didn't make sense to me?
I don't get it either.
All right, a battery is a storage of energy
Yep.
in a chemical form.
Mhm.
Okay, so it's chemical potential energy. And when the electrons are trying to get from one electrode to the other, the electrons start moving, and when they create electrical energy, because the electrons have the energy in them. And then they go through a circuit, and if you've got a globe in the circuit, you want the light. Yes, but we also know that they produce heat and sound. Right, so lights now are becoming nearly 100% efficient. You get very little wasted energy. Okay, but the older the light globes, you probably get more heat than light sometimes. Yep.
So does the GPE in a battery change to kinetic
Sorry?
energy?
The CPE, chemical potential energy,
So
that's
the
a C.
Yeah, so the CPE in battery changes to the kinetic energy.
which is electrical. Yep.
Through the moving electrons.
Moving of electrons. Well done. And the moving of the electrons goes on to, as it goes into light, we now have the moving of photons in the electromagnetic spectrum. Yep.
And that's just a flow diagram
It's just a flow diagram.
with like the wasted energy.
Yep. It depends. If the question wants you to include wasted energy, then do it. If it doesn't, then don't do it.
And that's how we should include it.
Yep.
Do the positive and negative ends of the battery have an effect on the transfer of energy?
No, the electrons will always go from the negative electrode to the positive electrode. That's why if you put two batteries the wrong way round, they just go energy straight from one battery to the other battery. It doesn't go through the circuit. That's why nothing goes. If you put that into a toy or like a remote controlled car, the car won't go anywhere because the electricity is going straight from one battery to the other, not through the circuit to get back to the other side of the battery. Yep. Right. So you need to be able to do these. And there are many circumstances